In this video, we'll discuss the parameterizations of affine varieties. And basically, the goal of this is to be able to describe all of the points of the affine variety V defined by the functions f sub 1 through f sub s, where f sub 1 through f sub s are polynomial functions and n variables x sub 1 through x sub n. So first, we're going to start with a few examples of parameterization. You've seen parameterization before. If you've taken multivariable calculus or even calculus 2 or even physics 1, you've seen examples of parameterization. Then we're going to define a rational function. I know you probably already know what a rational function is, but we're going to introduce the appropriate notation for algebraic geometry related to rational functions. And then we're going to come up with the notation or state the notation for the set of rational functions in m variables with coefficients in a field K. And then we're going to talk about the two ways to represent V. And I bet you can already think of them. We can represent this affine variety V in terms of the original functions, f sub 1 through f sub s, just setting each of those equal to 0. We could represent V that way. Or we could define V parametrically, as we'll discuss. And we'll talk about the benefits of each of those representations. And then we'll talk about two questions related to this idea of parameterization. One question is about parameterizing in the first place, and then one is about implicitization, or elimination theory. So this idea is if you do have some parametric or if you have rational functions or polynomial functions for a number of variables, the question is, can you find the original functions f sub 1 through f sub s? So this is kind of going in one direction. If you have these, can you always find the rational parameterization? And this is going in the other direction, right? If you have what ought to be a parameterization of something, can you find the original polynomial functions, f sub 1 through f sub s, if that parameterization, or if those stated equations involving rational functions actually leads to a system of polynomial equations that we can use to define a affine variety V, or an affine variety V. Okay, so let's just look at some examples of parameterization. Now, if you've taken Calc 2, you've probably seen this before. If you have an affine variety defined by the single polynomial y equals x squared, we could represent that this way. If we are in R2, this affine variety is a set of all points in R2 such that y minus x squared is 0, or if we add x squared to both sides, we have y equals x squared. So it's easy enough to draw this. It's going to give us a parabola. It's going to look like this. Now we can come up with a parameterization of this pretty easily. If we just let x equal t, well then y would equal t squared, because y is whatever x is squared. So that's a parameterization of this curve. As t increases, x increases. So we might add some arrows for orientation. So we could represent this curve in one of two ways. We can represent it this way, by the set of parametric equations, or we can represent it by this rectangular equation, y equals x squared. The variable t is called a parameter. It doesn't necessarily have to represent time, but it often represents time. And these two equations together form a parameterization of this curve. So it's a set of points x of t and y of t. And it was really easy to find a parameterization for that. You just let one of the variables be t, and then the other one was defined by the equation that we had at the very beginning. So this is one representation, and that's another representation. Here's another example. We have the variety given by this equation, x squared plus y squared minus 1. Assuming that we're interested in two-dimensional space where our field is the field of real numbers, we have x squared plus y squared minus 1 equals 0. And if we add 1 to both sides, we get 1. Hopefully you all look at that and you say that's a circle of radius 1 centered at the origin, and it is. So we have that there. So one way of representing this variety is just to state x squared plus y squared equals 1. Another way is to come up with a parameterization of this. Here's our first parameterization. If you've taken trig, you can probably think of it, or calculus. You've probably used this parameterization many times. To parameterize a circle or an ellipse, we tend to use a constant times cosine of t for our x value and a constant times sine of t for our y value. Those constants are the same. That's going to give us a circle with a radius equal to that constant. So these are the parametric equations for a circle of radius 1, which I think makes sense because this is saying that the x values oscillate between -1 and 1, and that's what we see on our circle. And the y values oscillate between -1 and 1, and that's what we see on our circle as well. And as t takes on all values, all real number values, we trace out the circle in this direction. And this actually covers the entire circle. Every single point on this circle can be represented by these parametric equations for a particular value of t, where t is a real number. Now, we could just trace out this circle for t in the interval from 0 to 2 pi. Then we would only trace out the circle once rather than infinitely many times. Or we could change this cosine of t and sine of t to cosine of 2t and sine of 2t, and we'd go around twice as fast. There are lots of different ways that we could parameterize this circle. Now, another parameterization is a little less familiar. And this is called a rational parameterization. Here we have x equals 1 minus t squared over 1 plus t squared, and y equals 2t over 1 plus t squared. Now, it's not obvious that this parameterizes that circle, but if we square x and we square y and we add them together, I bet we're going to get 1. Now, this turns out to not trace out the entire circle. This x value will never equal -1. There's no t value that we can substitute here so that this ratio is going to be -1. It's just not possible. We're never going to get this point, that point there on the circle or in the parameterization given here. But with this parameterization, we can get all the points on the circle. So this is a parameterization for V. Then it happens to exclude the point x equals -1, y equals 0. Oops. Now, if you're not sure that that satisfies that equation, you could just take the x and square it and the y and square it and show that you get 1. I think I will do that. So we've got this fraction. We're squaring it, and then we have this fraction. We're squaring that. Square the numerator and square the denominator. Same thing over here. When I square the 2t, I square the 2 and I square the t, so I have 4t squared there. We have a common denominator, so we can just add the numerators. And this, of course, if we distribute, gives us t to the fourth minus 2t squared plus 1 plus 4t squared. The negative 2t squared and the 4t squared give us a positive 2t squared. And that gives us a t squared plus 1 quantity squared in the numerator and a t squared plus 1 quantity squared in the denominator. And of course, that's equal to 1. So it's easy to check that these two parametric equations satisfy the equation of the circle. Maybe it's a little less obvious that this excludes the point -1, 0. But if you were to graph this rational function for t, you would see that there's no way that this will ever give us a -1. We avoid the line y equals -1 on the graph of that rational function. Now this one could be 0 when t equals 0, but when t equals 0 here, what we get over here is x equals 1, not x equals -1. So keep that in mind. Okay, so we've got two different parameterization. Obviously, x squared plus y squared equals 1 there, because cosine squared plus sine squared, when the angles are the same, that equals 1. Two different parameterizations here of our circle of radius 1. Now you might also see something like this, and this will sort of remind you of our discussion of dimensionality from earlier. If you have a variety defined by two linear functions in 3 variables, linear polynomial functions, so that means our x, y, and z are all raised to the first. Well, this is a set in 3-dimensional space because we have 3 variables. And let's assume that our field is the field of real numbers R. And we want this equation to be 0 and this equation to be 0. If we take this and we add the 1 to both sides, we get x plus y plus z equals 1. And then we also want this to equal 0. If we add the 3 to both sides, we get x plus 2y minus z equals 3. Now, since we have 2 equations and they're independent equations, there's not an equation here that's redundant, it's just a multiple of the other one. In 3 unknowns, our expectation is that the dimension of this variety would be 3 minus 2. And that's because we have independent linear equations and we've taken linear algebra. And I think that that makes sense. This represents a plane and this represents a plane. Those planes are not parallel to each other. They're not identical planes. So there is some perspective where the first plane looks like this and the second plane looks like, they're not necessarily at a right angle. I'll just make them look like they're at right angles. Are they at right angles? Well, it doesn't matter. Like we could test that, but I'm just gonna say that that's an angle theta and it's not necessarily a right angle. But you've got this plane and this plane and you have this, that's a really bad picture. I hope you get the idea. So they intersect and they intersect along a curve. And since we're talking about planes, that curve happens to be a line. If we want to completely describe that line, it's actually relatively easy to do. If you've had linear algebra, or even if you've just had pre-calculus, you probably know how to solve this system of 2 equations with 3 unknowns. Since you have 2 equations and 3 unknowns, that means there's going to be 1 free variable. So when I say 1 free variable, that's going to be represented by that parameter t so that we can trace out this line eventually. Or in other words, once I know what x and y are in terms of z, then I can parameterize the whole thing. Well, maybe I'm not explaining this very well. Let's call this the first equation and not our second equation. If we want to simplify this a little bit, we might want to get rid of one of these x's. So we might multiply the second equation by -1 and then add them together. And I know we've got a plus and a minus there. Some people might have a problem with the way I'm writing that. So we have this equation. Now this is relatively easy to solve for y in terms of z. I'll just multiply both sides by -1 and then add 2z to both sides. And I get y is equal to 2z plus 2. So now I've got y in terms of z. If I want, I could also take this system of equations and try to get x in terms of z by eliminating y. Well, to do that, I think I'll take the first equation and I'll multiply it by 2. So I'll have 2x plus 2y plus 2z equals 2. And x, actually, let's use the -1 times the second equation here. Negative x minus 2y plus z equals -3. Then when we add these together, the y's reduce and we just have x plus 3z equals -1. And we can easily solve that for x in terms of z. And we have this. Now, because we know what's coming, we know we don't need to try to solve for z in terms of x or y. Z is free to be anything. So what I would recommend you do at this point is just let x equal, or let z equal t. Then if z is equal to t, x is -3 times t minus 1, and y is 2 times t plus 2. And now we have parametric equations that describe that line, which makes sense. These are very similar to the parametric equations that we've seen already in calculus 3. Might have x naught plus at here, y naught plus bt, and z naught plus ct, where a, b, and c are the components of the direction vector of the line, and x naught, y naught, z naught is a point on the line. This has that form. I've listed them in the different order. I put z first because I wanted to let that be equal to my parameter. But you can see that if x equals this and y equals this and z equals that, it's just another version of that. So these are parametric equations for that line of intersection of this plane, or the graph of this, which is a plane, and the graph of this, which is a plane. So the affine variety described here is given by this set of parametric equations, and those parametric equations happen to be polynomials. So we have some concrete examples now of what parameterizations look like. Generally, our variables, the variables that we're interested in here, x, y, and z, rather than having equations involving x, y, and z like we originally had them, we have x, y, and z by themselves on one side, and we have them written as functions of another parameter. In this case, we have a parameter t, because the object that we're looking at is actually one-dimensional, which just means it can be traced out as t takes on infinitely many values, as one variable takes on infinitely many values, or one variable takes on a range of values. This is also happens to be one-dimensional, so the parametric equations are defined in terms of t, and this is one-dimensional. So our parametric equations can be defined in terms of t here or in terms of t there. But if you've had calculus 3, you know that we don't just have parameterizations of one-dimensional objects. We also have parameterizations of, excuse me, two-dimensional objects. So maybe you're interested in a sphere. So we've got b of x squared plus y squared plus z squared minus 9. So that's an affine variety. That's a set of all ordered triples in three-dimensional space, such that this minus 9 is equal to 0. If we add the 9 to both sides, we get that. And so that's a sphere of radius 3 centered at the origin. Now you might be thinking to yourself, how can I parameterize something that looks like this? Well, it turns out that there are some sort of standard parametric equations for a sphere, and they come from spherical coordinates. If the sphere has radius 3, we're going to have a factor of 3 for all of these guys. Z is usually written as 3 times cosine of some variable. Often it's that angle that we're making with that positive Z axis, but I'm just going to call that U. And then the other two guys involve cosine and sine of a different variable V. And then, oops, sine. And then each of those are multiplied by sine of U. If you take each of these guys, if you square them and add them together, you're going to get 9. So that is one parameterization of the sphere of radius 3. It's not a solid sphere, it's just sort of the outside of the sphere. Like if you're looking at a basketball, it's just the sort of skin on the outside, it's not the interior. Yeah, you can square those and add those together and you'll get 9. And the parameters U and V are roughly related to latitude and longitude. So I'm not going to go over that here, but if you do square the X, the Y, and the Z and add them together, you'll get 9. Before we talk about parameterizations involving rational functions, like the polynomial functions that we have here or the rational functions that we have here, we need to define a rational function and the notation that we'll be using for rational functions in algebraic geometry. And so here's a definition. It's definition 1 in section 1.3 of the ideals, I think it's ideals, varieties, and algorithms book. It says, let K be a field. Then we're going to define a rational function in the variables t sub 1 through t sub n with coefficients in the field K to be a quotient. So it's a quotient F over G, where F and G are polynomials with coefficients in the field K in the variables t sub 1 through t sub m. And of course, G is not the zero polynomial, meaning it doesn't have coefficients of 0 for all of the powers of t. So that's our definition. And we're going to say that two rational functions f over g and h over k are equal, provided that the following is true. If you cross multiply, you'll have f times k equals g times h. And both of those would be polynomials in this polynomial ring. If those are equal to each other in the polynomial ring, then these rational functions are equal to each other. And then finally, we need notation for the set of all rational functions in t sub 1 through t sub m with coefficients in k, and that's represented this way. Now I know this looks very similar to the notation that we're using for the polynomial ring over here. But notice that with the polynomial ring, we're using brackets. With the set of rational function, we're using parentheses here. Now, this set of rational functions is actually a field itself. And I think it's obvious why that's true. If you have rational functions, they satisfy the associative property of addition and multiplication. So you can group rational functions in any order. As long as you have a finite sum, you can change the grouping and you still get the same result. They satisfy commutativity, which means that one rational function times another rational function, that's going to be the same no matter what the order is. F times G is the same as G times F. The distributive property, excuse me, holds. We have a zero polynomial or a zero in the set of rational functions and an identity element 1 in the set of rational functions. It's the same as the zero polynomial and the multiplicative identity for the set of polynomials. And then we've got the additive inverse. If f over g is a rational function, its additive inverse is just -1 times f over g. You can add those together and you'll get 0. And then this is where this is more than a commutative ring. It satisfies that last property of a field, which is the multiplicative inverse property. For every rational function out there, there's another rational function out there so that you can multiply those two rational functions together and you get 1. So if I have f over g, and its multiplicative inverse is just g over f. And we can get 1 from that. So this is a field. The polynomial ring is just a commutative ring, but this is actually a field. Because we can divide rational functions and get other rational functions. 1 over a polynomial is not generally a polynomial. Okay, so we've got that, we've got the definition of equality, and then we've got the new notation. All right. So far, we've looked at examples of parameterization. We defined rational function, and then we talked about this set of rational functions in m variables t sub 1 through t sub n with coefficients in the field k. Now we have two ways to represent v in terms of the original functions f sub 1 through f sub s, and in terms of an implicit representation, which is usually a function of t or a function of t sub 1 through t sub m. So let's say that we are, before I do that, let me write this down. The first way to represent v is through the implicit representation. And so this is your set of polynomial equations. So you have f sub 1 of x sub 1 through x sub n is equal to 0. And the second polynomial evaluated at x sub 1 through x sub n is equal to 0. And then finally you have the s polynomial, excuse me, evaluated at x sub 1 through x sub n is equal to 0. And v, remember, is just a set of solutions to this set of s polynomial equations and n unknowns. That's called the implicit representation of V. Now, we'll say that a rational, and we're assuming that we're in n-dimensional affine space. So these depend on the variables x sub 1 through x sub n. A rational parametric representation of V can be written this way. Here we're going to have n rational functions, r sub 1 through r sub n, in the field of rational functions with variables, excuse me, t sub 1 through t sub m. And if we have those n rational functions, a rational parametric representation of V is given this way. It's the set of all points x sub 1 through x sub n that satisfy this. X sub 1 is equal to R1, evaluated at t sub 1 through t sub m. X sub 2 is R2, evaluated at t sub 1 through t sub m. X sub n is equal to R sub n, evaluated at t sub 1 through t sub m. The parametric representation is this, where all the variables that we're interested in, those variables that define the solutions to the original system of equations, are given in terms of some parameters, which we're calling t sub 1 through t sub m. This is, we'll say that the parametric representation of V consists of these rational functions such that the points given by these equations lie in the set V, and we require V to be the smallest set containing these points. We're going to return to this idea of being the smallest set in chapter 3. So don't worry too much about that. A couple of other things that we should know about the rational parametric representation of V is that this may not cover all of V. These equations may not include every point in V. So if A satisfies these equations, it's in V, but there might be some points in V that aren't actually satisfied by that set of parametric equations. And that's kind of like this point, -1, 0 that we mentioned earlier. When I take x and I square it, and I take y and I square it, it turns out when I do the simplification, I get 1. And as t takes on a range of values, we do go around this circle. We get all the points on the circle except for that one. But this is still a parametric representation of V. It just doesn't include all of V. V includes all of the points described by these parametric equations, but it also includes that point. If we want that point, we would have to use this parameterization instead. Okay, now sometimes these parametric equations R sub 1 through R sub n are not just rational functions, but they're polynomial functions. In that case, instead of calling this a rational parametric representation of V, we would call it a polynomial parametric representation of V. Okay, so now we have two different ways to represent V. We can represent V implicitly with the original equations, or those original polynomial functions in x sub 1 through x sub n set equal to 0. And remember that V is the solution set of that. Or we can represent the solution set in this way. It's the same thing as what we've been talking about before. We can represent V as y equals x squared, or we can represent V by this parametric representation given by x equals t and y equals t squared. Or here we can represent the circle in terms of this equation, x squared plus y squared equals 1, or x squared plus y squared minus 1 equals 0. Or we can represent it in this way or in this way. Both of those are parametric representations of that circle. And then here we can represent this affine variety by using these two linear equations that represent planes, or we can represent that variety using this parametric, these three parametric equations that describe that line of intersection of that plane and that plane. So you see we have two different ways of representing V. There are good reasons for using both of them. One reason that we like the parametric representation of V is because this is very easy for a computer to graph. All it has to do is take on different values for t, and it plugs t into over here, and it gets these values, and then the computer is able to easily find the ordered n-tuples that satisfy these equations up here. So one benefit of this is that makes these equations, make V easy to graph. So if I wanted to graph y equals x squared and I didn't know what that looked like, I could plug in t equals 0 here and here, and I could plug in t equals 1 here and here, and t equals 3 here and here. And then we could find out what ordered pairs we have, and then we could just trace out that curve. The same is true here. We could take on different values of t, substitute those into those equations, and even if we didn't know that this gave us a circle, as we graph x of t and y of t for different values of t, we would see that we're tracing out a circle. Same thing here. If we plug in different values of t here, we would see that different values of t actually give us ordered pairs that lie in that circle. So this is really easy to graph. Now, this representation is better when we're trying to determine whether a given point lies on the surface. So I might use this one when we're trying to determine whether a given point, a sub 1 through a sub n, I said lies on the surface, but what I mean is whether that point lies in V. So the way you can tell here is just plug in that point to all these equations. If you get 0, then you're good. If you're trying to use these to determine whether that point is in V, you would be replacing x sub 1 through x sub n with a sub 1 through a sub n, and then you'd have all of these equations. It's a little bit harder to see. Let me give you an example of that. So this is an example from the book. It's on page 16 in the book. We're given a variety defined by x squared minus y squared times z squared plus z cubed. So this is going to be the set of all ordered triples in three-dimensional space, such that this polynomial in 3 variables is equal to 0. Let's see what that looks like by graphing it in CalcPlot 3D. So all I did was Google CalcPlot 3D, and this LibreText.org website came up. Paul Seeberger from Monroe Community College got an NSF grant to create this, probably for his Calculus 3 students. But here you can graph functions of 2 variables. You can graph z as a function of x and y. You can graph y as a function of y, or x as a function of y and z over here as well. And I believe that you can come up with an implicit surface. And this is where the equation involves x, y, and z, where z is not isolated. And that's what we have here. So we're going to have x squared minus y squared times z squared plus z cubed. And we want that to equal 0. And we don't want to see that one anymore. Oh, and we get this thing, kind of odd looking. We want to set this back up again. Sorry about that. Let me try again. Implicit surface, and we want x squared minus y squared times z squared plus z to the third is equal to 0. And maybe let's let x take on, well, actually, that's probably fine. Let's just have more cubes. So there we go. So we see this. It's interesting, isn't it? So it's intersecting along the y-axis here. It has these like wings. It kind of reminds me of Dumbo a little bit. And then it has these sort of flat pieces. They're flattish. They look flatter than the top part, where x is positive and where x is negative. And then we see that it has this little like sort of, it looks like a cave to me, like a little part of the surface that you could sort of go into right there on the y-axis. And then I think we have something similar on the z-axis if you look at it over here on this side. So that's the graph of this particular parametric surface, or excuse me, not parametric surface. This is the graph of this particular affine variety. Now, it can be represented one of 2 ways. It can be represented this way, and we call that the implicit representation of that variety. Or it can be represented by these parametric equations. Now, I'm not going to show you here where these come from, but we have t times u squared minus t squared as our x value. Y is just equal to u, and z is equal to u squared minus t squared. And if we graph these together, we get the same surface as we have over here. So if I want to graph this, rather than trying to graph this, I might prefer to graph this. Let's try to graph this using CalcPlot3D as well and see if we get the same thing. Okay, so this was the implicit surface defined by that polynomial equation. That's our implicit representation of the affine variety. And now we want to graph this as a parametric surface instead. So all I did is I went up to this menu and I chose parametric surface, and then I got a set of equations that look like this. These are actually the parametric equations of a sphere of radius 2 centered at the origin. But that's not what we want this time. We want to use the parametric equations that were given to us. So we have t, or our x value is, okay, it says, gotcha. I don't want to graph it yet. I have t as x, y, and z over here as functions of t and u. They're using u and v. So everywhere I see a t on these equations, I'm going to replace it with a v. So I have v times u squared minus v squared. And then down here I have a u, and then I have u squared minus t squared, or v squared, sorry, because v is playing the role of t. And we want our u and t values to go between -1 and 1. And again, I'm using this range of values because those were the range of values used by our textbook author when they came up with their graph of this surface. So this is what it looks like when we use the implicit representation. Now let's use the parametric representation. Ooh, look at how much cleaner that is. Isn't that nice? Much cleaner. Okay, let's skip out on this and then do this one again. We've got x between -2 and 2. Maybe we just want x between -1 and 1. And y between -1 and 1. Okay, stop rotating. Cut it out. Let's see. Let's let z go from -1 to 1 is fine. And we get sort of a weird version of that surface. Oops, it's because that y value is going to 2. There we go. So that's what that looks like when we use the implicit form and we let x, y, and z go from -1 to 1. Over here, we'll use the parametric form, and we sort of get a prettier version of it. But it's the same thing. I hope you can see that it's the same thing. And we have the little loop here on the side, and we have the sort of flat pieces. There's a little bit of concavity to them. They're not completely flat, but they're much flatter than these sort of rounded pieces at the top. But the idea is that hopefully you see that this surface and this surface are the same surface. Now, if you want to check and be sure that this parametric representation satisfies this equation, all you would have to do is square x, square y, and then multiply it by z squared, and then cube z, and then show that everything cancels and you just get a 0. We could do that, but I'm not going to do that here. Now we also saw that this graph, the graph that was derived from the parametric equations, was graphed quickly. It was much nicer and cleaner than the graph that we got when we were using this equation. And that was defined as one of the benefits of the rational parametric representation of V. It's easy to graph on the computer. And we saw how much better the graph was when we were using that parametric representation. Now, I also claimed that if I'm trying to decide whether a point actually lies on the surface or whether a point actually belongs to the affine variety, it's easier to substitute here as opposed to substituting here. So let's illustrate that point down here. Here's a question. Let's say somebody asks you, is the point x equals 1, y equals 2, z equals -1 in the affine variety V? Well, you've got two ways of showing that. You can either set x, y, and z equal to 1, 2, and -1 over here, and try to find the values of u and t that might make that happen. Well, that's pretty nice. We immediately find out that y is equal, or the y value, which is equal to u, is equal to 2. So we know that u equals 2. So we can substitute u equals 2 and up here, and we have 1 equals t times 4 minus t squared. And -1 equals 4 minus t squared. So from this one, we can find out what t squared has to equal. So we have, if we subtract 4 from both sides, -5 must equal t squared. So, or -5 must equal -t squared. So t squared must equal 5. Okay. So t would have to be plus or minus the square root of 5. Now, if we substitute that in up here, we'd have 1 equals t times 4 minus t squared, which is 5. So we'd have -1 times t is equal to 1, so t must equal -1. Well, if t equals -1, t can't equal plus or minus the square root of 5, so there's a contradiction there. So x, y, and z can't equal 1, 2, and -1 at the same time because there's no value of t, or there's no ordered pair for t and u such that all 3 of these equations are satisfied at the same time. If this equation is satisfied, then this equation has to be satisfied. And then if t squared is equal to 5, then we get up here and we see that t would have to equal -1. If t squared equals 5, t is definitely not -1. So that's not going to work. So using the parametric representation, we can say, no, that point is not in the variety. Or since there is no ut such that x of u and t, y of u and t, and z of u and t is equal to 1 to -1. That 1 to -1 is not in the affine variety V, where we're saying, in other words, it's not a solution to this system of 3 equations that defines the affine variety V. You could do that. Or what's the much easier way? If I'm trying to determine if x, y, z equals 1 or 1 to -1 is in this variety, I could just substitute that point into the one polynomial equation and see if I get 0. So if I replace, my polynomial equation looks like this. Now, if I replace x with 1, I have 1 squared. And if I replace y with 2, I'll have 2 squared here, and z with -1. This is what I'll get. And if we do this arithmetic, we get 1 minus 4 minus 1. So that's 1 minus 5, which is -4. That's not equal to 0, since substituting x equals 1, y equals 2, z equals -1 into this equation doesn't give us 0. We know that that point is not in the affine variety V. So using the original system of equations, which was just a single equation in this case, was much, much better for determining whether a given point lies in the variety than using these equations. So you can see you can do it with these equations, but why would you? And this one is so much simpler. So again, our implicit representation is one of the best ways to determine whether a point actually lies in the affine variety V, whereas the parametric representation draws some beautiful graphs and draws them quickly. But this parametric representation may not include all of the points of V, yeah, that is a downside of that parametric representation. And it's also not very good at allowing us to determine whether a given point lies in the variety. Okay, so we've talked about a lot of things already. We've talked about the 2 ways to represent V implicitly and using parametric equations and the benefits of each of those. The last thing that we'll talk about in this video are 2 questions related to parameterization. Here's the first question. And we can think of this as the parameterization question. The question is, does every affine variety have a rational parametric representation? And the answer to that question is no. We have a term for that. And I'm not even sure that I'm pronouncing this right. I've just read about it in a book. I'm going to call it unirational, but I may be mispronouncing that. We say that an affine variety that can be parameterized with a rational parametric representation is unirational. And in general, it's not easy to just look at f sub 1 through f sub s, those defining equations for the affine variety, and decide whether a function is unirational or not. So no, not every affine variety has a rational parametric representation. And then it's really not easy to tell on the surface just by looking at the polynomial equations whether a particular affine variety has a rational parametric representation. So that's the first question. Does every affine variety have that representation? And we're going to say no. The second question is sort of going in the other direction. Here, it's as if we have the polynomial functions f sub 1 through f sub s, and we're asking ourselves, can we get a rational parametric representation? Here we're going the other way. And this says, given a rational parametric representation of a variety, or not even a rational one, just given a parametric representation of a variety, can we find the original equations, f sub 1 through f sub s? Or in other words, can we find the implicit representation of V? And the answer is yes, actually, with this one. So no, we don't always have a rational parametric representation. But yes, if we do have a parametric representation, we can find the original polynomials. And you've done this before. If you've taken Calculus 2 or Calculus 3, the strategy is usually called elimination. You can use elimination, sometimes called elimination theory. To find an equation involving the variables that you're looking for, x, y, z, however many variables there are, just an equation involving just those variables rather than the parameters. So we don't want any of the parameters there. For example, simplest example, if you have x equals t and y equals t squared, well, you can replace x with, or you can replace t with x down here and you get y equals x squared. And so now we've got a polynomial equation, y minus x squared equals 0. So that means the solution set of this equation, which corresponds to the solutions given by these parametric equations, is just this affine variety. Or when we have x equals cosine of t and y equals sine of t, if I take those and I square them and I add them together, cosine squared plus sine squared, we all know from trig that that equals 1. So that corresponds to the affine variety x squared plus y squared minus 1, or the affine variety defined by that single polynomial in 2 variables, x squared plus y squared minus 1 equals 0. Here's another example. If you have x equals 1 plus t and you have y equals 1 plus t squared, in order to eliminate the parameter t, we might solve this first equation for t in terms of x. So we'll have t equals x minus 1. And then since we know that t equals x minus 1, we'll replace this t with x minus 1. And so we get that. And if we want, we could expand this expression over here. And we would have y equals x squared minus 2x plus 2. Now the corresponding affine variety would come from setting this equal to 0. So we'd have y minus x squared plus 2x minus 2 as a defining polynomial for that affine variety v. But these parametric equations correspond to this rectangular equation, and that rectangular equation corresponds to this affine variety. The solution set of this equation is the same as the affine variety, and the affine variety is also described by those 2 parametric equations. But the idea is we're just trying to get rid of the parameter t. Now, we did look at some parametric representations that involved 2 variables. We said if we had a sphere of radius 3, we might represent it this way. Oops, that should be a sign of u as well. Now, the parameters here are not t's, but they're u's and v's. That's the same thing. That's fine with us. If I take the x, the y, and the z, and I square them, then I can get rid of all of the u's and the v's. If I take those and I add them together and square them. So if I take my x and I square it, I get 9 cosine squared v sine squared u. If I take my y and I square it, I get 9 sine squared v sine squared u. For the z, if I square that, I have 9 cosine squared u. And then we can factor out the 9 from everything. And then maybe for these 2 guys, let's factor out a sine squared u as well. 9 times sine squared u times cosine squared v gives us our first term. And 9 sine squared u times sine squared v gives us our second term. And I'm sure that this is all very familiar to you from calculus 3. That's equal to 1. And now I have 9 sine squared of u plus 9 cosine squared of u. If we factor out the 9, we've got sine squared u plus cosine squared u, which equals 1. And so we have the equation x squared plus y squared plus z squared equals 9. All of the points given by these parametric equations are described by this rectangular equation. And those are 2 different ways of describing the affine variety v given by this single polynomial equation in 3 variables. And again, this is a sphere of radius 3 centered at the origin. Okay, so see what we did there with the trig functions was we squared these and we used trig identities in order to get rid of the parameters u and v. Here we solved for t, and then we substituted to get rid of the parameter t. Here we squared those and we used a trig identity again, a Pythagorean identity, and here we solved for t, but it was already solved for because we knew x equals t, and then we made a substitution, and that got us there. So the idea is that we just eliminate the parameter or parameters until our final equation or equations only involve x sub 1 through x sub n. So I said find an equation involving that, but we should say in general, we want to find maybe more than one equation involving x sub 1 through x sub n, and that has none of the parameters in it, t sub 1 through t sub m. So I think that's it for this video. We talked about examples of parameterization, the definition of a rational function, and the notation that we use for the set of rational functions and m variables with coefficients in a field k. It looks very similar to the set of polynomial functions and n variables with coefficients in a field k, but the set of rational functions happens to be a field itself. And then we said that there are two ways to represent v. One is the implicit representation, f1 equals 0, f2 equals 0, all the way through f sub s equals 0. And the other one is the parametric representation. Parametric representation is great for graphing, and the implicit representation is great for determining whether a point actually lies in V. And then we said, okay, there are two questions. Given this, given f sub 1 through f sub s, can I find the parametric representation every time, a rational parametric representation? And the answer to that question is no. For the second question, implicitization, I'm having trouble with that every time. Implicitization, that's just saying if we have the parametric equations describing V, can we find f sub 1 through f sub s? And generally we can, and usually that involves eliminating the parameters t sub 1 through t sub m, which may be represented by different letters like u and v. That's what we saw in our Calculus 3 courses. So that's the end of this discussion. Next time we'll come back and we'll talk about using geometry to parameterize varieties.